So indeterminate forms look like this, where if you plug in a number into an expression, if you ever get like 0 over 0, or some kind of infinity divided by some kind of infinity, or the infinity is being added or subtracted, or rather subtracted like this, infinity minus infinity, or if 0. So anytime you get something like this, you have permission to use L'Hopital's rule, because these are considered indeterminate forms. And I believe these are actually most of the cases, if not all of them. So we keep an eye out for things that look like this. And I'll tell you now that the most popular ones that you'll see, it tends to be A and B. These are the most popular ones that we see, although these can come up as well. So let's try some of these problems. So let's look at example 5 here. Let me focus my camera on the letters. Let's see, so let's dive into this. Example 5. The limit as x approaches 4. If you plug 4 into there, it's going to be 4 minus 4, which is 0 times 3 is going to be 0. Plug 4 in here, 4 squared 6, it's going to be 0 over 0. So this is indeterminate form. So what we can do, we keep the limit, but we can take the derivative numerator and then the derivative of the denominator. You see, you do not apply the quotient rule per se, unless the numerator was a fraction in its own right or the denominator a fraction. But here it's just something over something. Take the derivative of the top, take the derivative of the bottom. The derivative of the top is actually just 3. The derivative of the bottom is 2x. And if you see how you can distribute, it'd be 3x minus 12. You take that derivative, it's just 3. Now let's try this again. Plug in 4 yet again, and you get back 3 over 8. And that'll be your final answer. Let's see. Yeah, because 3 over 2 times 4 is 8. 3/8, right? 3/8. So you always plug in the number and see what happens. If you get 0 over 0, or if you get any of these forms, boom, hit it with L'Hopital's. We did, and then we tried the number again, and it worked out. No problems here, totally fine. Let's try this. If you plug negative 4 in there, it's actually going to be 0. You plug negative 4, it's going to be 0 again. So 0 over 0, indeterminate form. Let's hit this with L'Hopital's. So carry your limit and take the derivative of the top, which is 4x plus 13 over 1. And if you plug in negative 4 in there, it should be, I think it's just negative 3. Yeah, that looks good. Now down here, so if you plug 6 in there and there, you're going to get 0 over 0. So I suppose you could hit this with L'Hopital's rule. And you know what? I probably will, but I just want you to know that there's actually a different way of doing this problem. We'll get there. For now, let's just try L'Hopital's rule. So let's see. The derivative of the bottom is just 1. The derivative here, well, the derivative of that is nothing. It's just 0. So really it boils down to the derivative of this expression or this term. That would be 1/2 x plus 10 to the negative 1/2 times 1, right? Because square root is the same as the power of 1/2. Right there, keep the inside the same, subtract 1 from 1/2, negative 1/2, and you multiply by the derivative of the inside, which is just 1. Now let's plug in 6. So we get 1/2 16 to the negative 1/2. That's the same as 1/2, and then the square root of 16 at the bottom. That should be 1/8 actually. I am going to fly through these. Let me know if any of these are incorrect, but I'll try to be careful here. Let's take one more quick look. Yeah, I believe these are good so far. So let's keep going here. And don't be surprised if most of them, if not all of them, are L'Hopital's rule. But let's see. I think we're going to have a different case coming up here. So let me focus my camera yet again, just to make sure it looks good. Number 8, plug in 0. Keep in parentheses. Plug 0 there. You actually get back 0 over 0. So let's hit L'Hopital's rule. Equals limit x approaches 0. Oh, you know what? Let me go back. Let me make a quick comment here. Remember I said that there's actually a different way of trying number 7. A different technique you can do is to multiply top and bottom by the conjugate of this expression, which would be the square root of x plus 10 plus 4. You switch the sign. You can multiply top and bottom by this expression, and you will get the same conclusion, 1/8. But you don't have to do this technique for this problem. Sometimes you do have to do this technique, but I don't think we'll have to do that tonight. Maybe we'll save that for a different video. All right, as we were. So let's see, derivative of the top is cosine 6x times 6, because it's the chain rule. Derivative of sine is cosine. Keep the inside the same. Multiply by that derivative, which is just 6. All over 4. Plug 0. That's a 0, Mr. Lee. Plug a 0 in again. We get cosine of 0 times 6 over 4. So the whole answer is 3 over 2. Plug 0 in there. 6 times 0 is 0. Cosine of 0 is 1. 1 times 6 is 6 over 4. 6 over 4 reduces to 3 halves. Now look, 9 and 10 are different. Notice for all the problems we've done today, x was approaching a finite value. Finite value, finite, finite. Here, x is approaching the infinities. And a lot of times that happens when you have what we call a polynomial divided by a polynomial, which is called a rational expression. And a lot of times, again, there are different techniques that you can employ from pre-calculus, but why don't we treat this like any other? If you plug in infinity into here and into there, what are you going to get back? You're going to get back like infinity squared times 5 minus. So that would be kind of messy because you would probably get something that's like infinity minus infinity. So I'm tempted just to hit this with L'Hopital's, but let me show you a technique that you may have seen in class. What I'm going to do is, if you look at the denominator, the degree of the denominator is 2. It's x squared. So what I'm going to do is I'm going to multiply top and bottom by 1 over x squared. I think you may have seen this in class. Let's see what happens. And again, I'm using x squared because that's the largest power from the bottom was a 2. And if I distribute, and if I simplify, I get back this. Limit as x approaches infinity of, now, so let's distribute 1 over x squared to that. That'll just be 5 minus 3 over x plus 1 over x squared. In the bottom, it'll just be 3 minus 5 over x squared. Now watch what happens. If I plug infinity into there, it's going to be 1 over the square of infinity. And I can write this out for you if you want. So let's run through this, and then I'll show you how to do this problem like in 2 seconds. But your teacher probably wants you to understand how to do this the long way, which is basically what I'm doing. Check it out. 3 divided by infinity. Let me tell you why that's basically 0. If you have $3 and you divide it or split it into an infinite amount of pieces, imagine $3 and you divide it into the population of the world. Everyone gets nothing because there's a lot of people. And $3 divided into a lot of people, it's nothing. And infinity is much bigger than the population of the world. So that's 0. These are definitely 0. So the answer is just 5/3. And you could have seen that by looking at the original problem right here. See that 5/3? It was staring at you from the very beginning, but that's only because it was x squared on top and x squared on the bottom. If the top and bottom have the same degree, then all of the smaller inferior pieces can be ignored, and you just look at the coefficients of those leading terms. But that's only if the top and the bottom have the same degree. That's not always the case, like for instance down here, we'll get there. So again, for this problem, we plugged in infinity, and then we did this trick where you multiply by the reciprocal of the strongest piece from the bottom. And then you did this little gimmick, and you got this here. And I can think of other ways of doing this problem, but there's a couple of different ways. Now, let's try this one here. I can tell you just by looking at this that the answer is 0. And I'll tell you why. The bottom has a degree of 2. The top has a degree of 1. The bottom is going to outgrow the top. So the bottom is going to be huge, and the top is going to be not as big. So it's bottom heavy. Anytime it's bottom heavy, it's going to be 0. If you were to graph this on Desmos, I don't know what the graph would look like, but I guarantee you'd have a horizontal asymptote of 0 as you go to the right. What you can do for this problem is you can do the same gimmick. You can multiply top and bottom by 1 over x squared, because x squared was the strongest piece from the bottom. Do the same trick that we did here. You'll see that it's basically just going to be, let's actually do this. Let's distribute this, and that'll be limit as x approaches infinity. It's going to be 4 over x minus 3 over x squared over 5 plus 1 over x squared. If you send x to infinity, this is gone, this is gone, this is gone. It's just 0 split into 5 pieces, which is 0. So that's those ones. I did want to make a comment. 14 and 15 are a bit more technical. Let me know when you're there and I'll explain these ones to you if you'd like.